please elevate the Pad 4 launcher to nominals?
And work.
Thanks, sir.
OC check 81, 82, and 83.
CMLO.
Go ahead, hello.
Check item 92. Azimuth set to nominal settings. 354.0. Elevation 83.7.
MMCM on 2. Yes, sir. I'm sure you heard the yellow tell you that we're at nominal settings. Are you interested in performing a vertical here soon?
Yeah.
Take all the time you need, sir. RSM, CM on 2.
Go ahead.
I don't know if you copied that traffic I had with the MM, but we're thinking about doing verticals a little early. Are you able to accommodate?
Radar TM, can you all come in? Can you all accommodate that?
TM can accommodate.
Radar can accommodate.
Thank you very much. PI, CM on 2.
Go ahead.
You okay with doing the vertical here soon, sir?
Yes, that's fine.
All right, we'll let you know.
Thank you.
Go ahead, MM. Stand by, okay? OC, CM on 2.
Go ahead.
We'd like to perform the vertical check starting at step 9-6, but not starting the clock until 1:03.
We've recycled the clock to 10 minutes and holding for vertical checks on pad 4, like station checks on channel 2. RCV,
RCV go.
RDT,
RDT go.
TM,
TM go.
CI,
PIs go.
radar,
Radar go.
surveillance is go, PLC, SC,
FC is go.
PC, ACS, LO,
LOs go.
CUS,
Go.
MM, BS,
VS go.
PC, CM,
CM is go.
RSO,
RSOs go.
and range is go. OC check 96, 97.
TM check 99.
RCV check 98. FC check 100.
Got about 40 seconds. On my mark, we'll be at 10 minutes and counting for vertical checks on pad 4. 3, 2, 1, mark. We're at 10 minutes and counting.
TM check 105.
RCV 107 and work.
TM check 108. TM check 111.
Radar check 109.
TM check 112.
FC, CUS.
9 minutes.
This is FC, go ahead.
Please switch polarity.
Polarity switched.
TM, we don't see the spectrograph.
I'm going to put the decom back in measure mode, but I see your data coming along, so try latch it onto it again.
Okay, we'll recycle. FC, CUS.
This is FC.
Please revert to flight polarization.
I'm sorry, can you say again?
Please revert to flight polarization. TM spectrograph is good.
FC has polarization.
Copy. Confirmed.
Eight minutes.
CUS check 116.
RCV check 107.
Seven minutes.
PI check 119.
Hello, RSO. Wind-weighted launcher settings are azimuth 350.4, elevation 83.0.
Copy and work.
Check 115.
And RSO check item 120.
Six minutes.
Launcher is set. Azimuth 350.4. Elevation 83.0. LO check 121.
RSO concurs. Check item 122.
Five minutes.
Copy. Sent positive pitch, positive yaw. Reset. CUS check 124.
4 minutes.
RDT check 126.
Three minutes.
BS check 129.
TM check 133 and 136.
RCV check 138.
TM check 139.
Radar check 140.
2 minutes.
TM check 142, 143. TM check 145.
Okay. 90 seconds. RCV, here you go.
RCV go.
RDT.
RDT go.
TM.
TM is go.
PI.
Go.
Radar.
Radar go.
Surveillance is go. PLC. FC.
FC is go.
PC. ACS. LO.
LO's go.
CUS.
Go.
MM. VS.
BS go.
CM.
CM is go.
60 seconds. RSO.
RSO's go.
The range is go. $50. 40. 30.
ACS check 147.
20. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
VS check 152.
TM check 154.
ACS CUS. Please confirm ready for uplinks. SIM. CUS check 155.
Uplink sent. Uplink sent.
Reset. CUS check 156 CUS. Getting confirmation that we're all done up here.
Go ahead. Yes, good. Thank you.
Good test.
Reception's good. Radout's good.
Command was good. FC check 161.
RCV check 163. RDT check 162.
OC, CM on 2.
Go ahead.
We can reset the clock to nominal T time.
Clock has been reset. OC check 164.
Thank you.
TM check 167.
RF avoidance is now in effect on pad 1.
Radar copies.
OCRSO, check item 84. OCRSO, check item 84.
Mr. Live.
And today is day number 2 of the 2020 NASA Sounding Rocket Campaign. This feels very much, I feel like we're doing the America's Cup or something like,
That's right.
like that. Like
Yeah.
Australia and the United States
yeah.
at each other's throats here.
Semifinals now.
Day 2 of the America's Cup. But anyway, this runs through February 7th. The principal investigator for this mission is Scott Bailey of Virginia Tech. And he's preparing to launch a Black Brant 9 for the Polar Nitric Oxide, or Polar NOx mission. This live broadcast was funded through the NASA Space Science Education Consortium under a cooperative agreement with the University of Alaska Fairbanks. With me here tonight is Don Hampton. He's a research associate professor for the Geophysical Institute at the University of Alaska Fairbanks. And my name is Rob Prince. I'm an associate professor in the Communication and Journalism Department at UAF as well. And if you've been watching the live stream for a while, you have been hearing Range Director Kathy Rich running the countdown and mission personnel reporting back. Correct? Again,
That's right. Yep.
very similar to last night. If you joined us last night, unfortunately, we weren't able to launch the rocket. But tonight things are looking good again.
Yep.
Although the word was that last night the problem was nothing went wrong, and that was the problem, that we let Murphy in at the last minute. So I'm hoping that something you feeling good about tonight?
I'm feeling better about tonight, yeah.
Okay. All right.
I think whatever issue they had last night with the launch, they probably checked and checked again.
Okay.
So,
right.
And we're seeing, I think skies are clear. I haven't heard anything about the winds aloft, but my guess is they're probably just fine as well.
All right.
Yep,
so things are looking really good for tonight.
Yep.
I know I said that last night too. But
that's rocketry for you.
But
right?
yes. That's the way it goes. We got all the way down to 0, and unfortunately, the launch didn't happen. So tonight, looking for it to work. And so again, you can see we got the countdown here below us. That is not an exact time right now. This is what do you call this? Do you have a name for this countdown?
Well, I mean, so there is a countdown to when the window opens.
Okay,
and that's that's probably what this countdown is. I haven't actually looked at the timing.
Right.
It looks like right now they're aiming sort of for a 4:40 local time launch.
Okay.
But that could still be adjusted based on whatever they find during the test beforehand.
Right.
Yeah.
Okay. So that's the ballpark of what we're looking for here. We'll be giving you. What's that?
Speak a little lower and you speak a little louder.
Okay.
I'm supposed to be quieter?
I know.
You have a knob there you could turn down, but we're scared that what that might do. So okay, I will just be. But I'm excited, Don.
It is exciting.
It's hard for me to keep my voice down. Okay. Well, at any rate, we do have some folks who are monitoring social media channels, and I'm doing my best here to keep an eye on our YouTube channel, which you're watching right now. So if you'd like to comment on, or if you have any questions about what's going on tonight, we're doing a good job of keeping an eye on that and answering it. And I'm going to see if there are any that we can respond to here live on screen as well. And then, so feel free to check in for that. And then again, another reminder, if you're watching locally and you're hoping to step outside and see the rocket launch, there is approximately 30-second delay in this YouTube video. So as I said yesterday, this is not New Year's Eve.
That's right.
Don't wait till the last second. I'm not Dick Clark. You're not Ryan Seacrest.
I'm definitely not Ryan Seacrest.
And so do not wait until the last minute to step outside. As Don suggested yesterday, about T-minus 5 minutes is a good time to step out.
Yeah.
That'll give you time to make sure that you don't miss it as we build up to the countdown to 0. Now, one of the things that we're doing tonight that's a little different from yesterday is we're going to do a couple of test rockets. Is that the plan? So we don't have a countdown for that yet.
No.
But I am hoping we could. Apparently, they're not that amazing to see, but
they're not as exciting as the real rocket.
But there's something
that's why
to
they're
see.
test rockets, right?
So we might hear a countdown then for that coming up sooner.
Right.
So don't be confused. That's not the actual rocket that's going into space tonight.
And these you can't see from town.
Right.
You can barely see them on the range, so you can't see them from town.
Right.
As
we were talking about earlier, they're kind of like a glorified version of the Estes rockets that you shoot off in your various clubs.
They're about a meter long, and they go a few thousand meters up, and that's about it.
Okay. And what's the purpose of these test rockets?
Well, it's to test the system.
Okay.
There are several systems you can test with this. One is the clock itself. The numbers we're reading right now.
Mm-hmm.
There's a main control clock down the lower range, and they test that goes through its cycles. The tracking radars that track the big rocket, they can also test those during this time as well.
Okay.
And sometimes it's just something to do.
Right.
Not so much tonight, but
right.
but other nights when we've been sitting around for a week and a half and not much is going on, it's something to do.
That's good because
yeah.
It is about 3:22 local time here, right. So it's another late night for us. Down at the gate, let's see, it was just about 24 degrees below zero. Mm-hmm. So gate's a pretty good measure for what the pad's temperature is.
Yeah, very
correct?
Close, yeah.
Okay. And just again, a reminder, the rocket's vertical now, if you've been joining us on the YouTube feed before we started the commentary, and it is wrapped in styrofoam.
That's right.
To keep the temperatures consistent, so that you don't have two parts of the rocket at different temperatures expanding, contracting.
That's
correct?
Right. That's right.
Okay.
Yeah, because that can lead to cracking of the solid propellant, which could lead to not working very well.
Right. Yeah. Daniel, you want to take that shot here a second? If you have a minute, we'll get back to the vertical.
There we go. Yeah.
So we're vertical, which is great. The housing that is. Forgive me, would you call that a shed? I hate to disparage the thing that the rocket stays in. Do you have a fancy name for it?
We call it the enclosure, I think.
I'm sorry, the enclosure has backed off. If you watched last night, we actually had footage of the enclosure moving out of the way. It's a very kind of weird thing to see.
Yeah. Right.
Is to watch this building suddenly move. But we're already past that. The rocket's vertical.
Yep.
And so what are they doing right now since we've got, about an hour before we're thinking of launching?
Right.
What are they doing?
Right. So right after they took it to this vertical position, they went through what's called a vertical check, which is basically a countdown from T-minus 10 minutes all the way through what would be the launch and then a little bit beyond that. And what they do is they go through the checklist that we would run for an actual launch and check off all the items to make sure that all the components are working.
Okay.
So they check not only the payload, which is going to fly, but they also make sure that the command and data handling is working, and they test other aspects of the ground system as well.
Okay.
Yeah.
And it looks like, are we moving to the test rocket range now, or I guess I'm on a 30-second delay too. So,
right.
All right. But so the next thing that we'll hear are the test rockets. Now we talked a bit about this yesterday too, but I think it's good. It's just so fascinating to me, the multiple layers of safety concerns that have to be addressed and are addressed. Are we doing the weather balloons again tonight?
Yeah.
Okay.
So they're doing the weather balloons, and I got a nod from somebody saying that the winds aloft are good.
Okay.
But the point is that these rockets are completely ballistic. Once they leave the rail, we're not guiding them and trying to land on a specific spot. They go where they're going to go. And where they go is influenced heavily by the winds in the lower atmosphere. Especially the
That's
first.
because the rocket's traveling slower
It's
at the lower,
slower,
or there's stronger winds.
And the atmosphere is thicker.
Right. Okay.
Right. So,
all right.
a 50 mile an hour wind on the ground is much more of an impact than a 50 mile an hour wind at 100 kilometers altitude.
Right. Well, yeah. Too, if you think about the earlier on, the more impact it would have on the angle than if you're later. Okay.
Yeah, that's right.
Which I'm sure you have a sciencey term for, but
I don't have
I just use my finger and go like,
that's good.
If you're down here by my knuckle, it's going to really change it. But if you're up here,
you'd be surprised how often we use like pins and boxes.
Right.
It happens pretty good.
Right.
So so the balloons are to measure those winds, and then they have programs that they run that takes all the information from those winds and the temperatures and puts them in, and they figure out where all the parts of the rocket will come down.
Excellent.
And if they impact any place that is inhabited, we can't launch.
Right.
Now that launcher you saw a minute ago, it actually has two-axis control, so you can change the azimuth and the elevation.
Okay.
And they can try to adjust that so they can launch in a position that will not come down on anybody, which is most of the time. But if they can't, there's sometimes you just can't launch because of winds. But the indication tonight is the winds are not a problem, and we shouldn't have any issue with launching.
Okay.
Yep.
Excellent. So we have the weather balloons going up that are figuring out where the rocket's going to go. And this is more for safety than for the science part, or is this a part of making sure the rocket ends up in the right part of space?
It's primarily for safety.
Okay.
Right,
all right.
I mean, but I'm sure if one of the science team decided it was going too far off where they wanted to go, they would maybe ask not to launch then as well.
Okay.
So yeah,
right.
it's general decision making, but the main thing is for safety.
Right. So weather balloons, making sure that the rocket lands where they want it to land.
Yep. Okay.
We've also got that road that's 50 yards.
50 yards away from the launcher. So,
yeah.
So, yeah. And in fact, when they do these test rockets, will do the same thing. They will send out some roadblocks, one side of the Chattanooga Lodge, the other side a couple of miles down the road, and just ask people not to drive through while they're doing these tests.
Right. Okay. So we've got that element as well.
Yep.
Also, I guess we're on the horn with the Russians tonight too.
Not directly. We were on the horns with NORAD.
With NORAD,
who
right?
Were talking to the Russians. So yeah, we don't get to talk to the Russians directly, but but we are talking to NORAD, who does keep track of all the launches anywhere in the world, and maintains communication with our counterparts in Russia and other countries as well, saying we're launching a scientific rocket. This is not a missile, and so
right.
Please don't react in kind. Yeah, we're on that. We also have conversation with FAA to find out what high-flying aircraft might be going over from the East Coast to Asia,
right?
Because there are a lot of flights that go over. And then we also have a aircraft radar running all the time to look for smaller planes, smaller flights locally that might not be communicating directly with FAA.
Right. So there are a lot of moving pieces.
That's right.
Here. A lot of things that have to be considered,
right.
And so that's something that people are also working on right now, is making sure that all those pieces are in place.
They're paying attention to that, and they're monitoring all those systems as we go. Yeah.
Right.
And that's like John Hickman said the other day, that when we get these rockets on range here, we go from just a handful of people who work here all the time. In this case of this rocket, we probably have 35 to 40 people from NASA Wallops here doing that. If we've got multiple projects going on, we can have on the order of 100 people out at the range.
Okay,
yeah.
Great. And shall we talk a bit about the basic mission again, just a refresher for folks who maybe weren't tuned in last night?
Right.
The goal of this mission is to shoot this payload about 150 miles up into space, point it at a star, and then use the light from that star. You put that on a spectrograph, and we're going to measure the amount of nitric oxide in space at that point.
In the atmosphere.
In the atmosphere. So they're still in the atmosphere, even though they're in space.
Well, there's still a bit of an atmosphere.
Okay. All right.
It's very thin.
All right. And the idea being that this nitric oxide interacts with our ozone layer and kind of beats it up a little bit and it's activated by the aurora.
Right.
So
the nitric oxide we're looking for is that it's produced by aurora. When the electrons come down and bump into our atoms and molecules, they can also cause chemical reactions to happen, and that will get a nitrogen and an oxygen basically to join together. Nitric oxide in sunlight is destroyed pretty easily. But we're now in our polar night, right? So there's no real destruction mechanism for that nitric oxide that gets created up here this time. And the altitude it happens is about 60 miles up, about 110 kilometers or so.
Got it. Okay.
That's not where the ozone is, but because it's a long-lived species, it can actually migrate down to the region where in upper stratosphere where the ozone layer happens. And so the concern is if you have a lot of aurora and are producing a lot of this nitric oxide in the polar winter, that eventually you could have an impact on the ozone layer in the stratosphere.
Okay.
We have not had a lot of aurora because we're in our solar minimum conditions right now, and so what we'll probably be able to see is this will sort of be a baseline of how much nitric oxide is being produced in quiet times.
Okay.
Yeah.
Excellent. And we do have a video with the principal investigator, Dr. Scott Bailey, as well as Justin.
Are you ready for test rockets shortly?
Oh, okay. So we're getting ready for a 10-minute countdown?
That'll be a 10-minute countdown.
Okay.
So we can go ahead and watch the video.
We got a little time. So here's a video with Principal Investigator Scott Bailey. If Daniel, is that looking good? Okay. And co-investigator Justin Carstens from last week, where they're describing the experiment that's going to, we hope, occur tonight.
Hope to occur tonight, yep.
We're trying to measure a chemical, nitric oxide, that's created by the aurora and grows to large abundances in the polar night. We want to see how much there is and where it is, where in altitude. What's really interesting about this is we've measured nitric oxide all over the globe, but we usually measure it using techniques that involve sunlight. And nitric oxide is created by sunlight. It's also destroyed by sunlight. But interestingly, it's created by the aurora as well, and the aurora occurs in darkness. And at high latitudes, you have the long polar winter. And because we're using starlight, the way we would normally use sunlight in the rest of the Earth's atmosphere, we're using starlight as the light bulb. We need a star to be in exactly the right geometry. It needs to be in exactly the right place.
We'll be using Algenib on this mission. We're using that star because it's bright in the UV, and we need a UV light source. The payload has a UV spectrograph, which it measures light, UV light, at this particular color we need that is absorbed by nitric oxide. So we'll be looking at the star. It'll be filtered through the atmosphere, and nitric oxide will absorb a lot of that starlight, and how much of that starlight, the color it absorbs at, that'll tell us how much of it's between us and the star, so how much is in the atmosphere.
But there's a lot of physics between the creation of the NO and the destruction of ozone that we just don't understand. So measuring the nitric oxide, measuring the altitude profile, it's going to help us understand that, and that's what we're after.
So again, that was Dr. Scott Bailey, who is the principal investigator from Virginia Tech.
Yep.
As well as Dr. Justin Carstens, co-investigator from Virginia Tech as well. And yeah, we're seeing a few comments there. We got about 61 people at the moment on YouTube. I see that Russell Mitchell is saying I missed a rare opportunity to wear my spacesuit. This is my first rocket launch, and I wasn't sure where we wanted to go with this, but I chose not to wear my spacesuit, in part because it's still drying out from Saturday when I was at the North Pole Library and almost melted like the Wicked Witch of the West. It was so hot in that thing.
Yeah.
But thank you. I feel I was tempted, but I did not want to take away from the significance of tonight's event by dressing as an astronaut. I also didn't want to confuse people that this might be a live mission that I was about to walk out to.
Yeah, right.
Because, again, as we talked about yesterday, this would be an... this might be an understatement to say this would be an unpleasant trip.
It would be a very unpleasant trip, yeah.
For should we strap a living organism to this thing? And tell us a bit about why this would be so unpleasant.
Well, so because it's unmanned, the forces are quite extensive or quite severe. So it's well over 10 Gs on the acceleration, and it's very shaky.
Right.
So you know. Either of us riding on there would be a little bit shorter when we got done.
Right.
Quite a bit
can any of the extensive staff here Google how many Gs a human could survive, just out of curiosity? Somebody's.
I know that, you know, some of the pilots can actually do several Gs.
Yeah.
But that's a little bit more. I think it's more gradual going into it.
Right.
This is sort of
this is like bam.
This is bam. Yeah.
Which brings up another interesting point, that this is a solid fuel rocket.
That's right, yeah.
As opposed to a liquid fuel rocket.
That's right.
And liquid fuel is what's required if you're going to send humans into space, because it is a more gradual acceleration.
Yeah, and you can also dial it back. You can change the thrust on a liquid. Most solid propellants, and certainly the ones that we use, they're just on or off. They're binary.
Okay.
There are now, as I understand it, there are now some solid ones that are also somewhat controllable.
Okay.
But we don't use those here.
Right.
We just have the ones that turn on and go.
Yeah, right. And let's talk about what we're going to be turning on and sending into space tonight. It's a two-stage rocket.
Yep.
The first stage is a Terrier Mark 70, which is a military surplus stage.
Yep.
correct? Yeah. Okay. And then the second stage is the Black Brant 9, and that is a Canadian company that has produced that.
That's correct, yeah.
Why these two stages? Why not both Mark 70s? Is there something that each one does differently?
I think, yeah, they have somewhat different performance.
Okay. Is it like a low and high gear?
I think somewhat, yeah.
Okay.
And I think some perform better at different altitudes and that sort of thing.
Okay.
I don't know a lot about the details of the rockets themselves.
Okay.
They don't let me touch the rockets, which is probably a good thing.
Right.
But yeah, I think the lifting capabilities, the Terrier has to lift more than the Black Brant because it has to lift everything, whereas the Black Brant only has to lift the payload after it gets going. And the profiles on how what the thrust is there we go.
Okay.
And there's a picture of the payload itself, actually. So.
All right.
And
so that's just the payload, because
the payload
this whole thing from tip to tail is just over 57 feet.
That's right.
And so this is just the payload, which is about 25 feet.
That's right. Right.
Okay. So that gives you a sense of what the size of the rocket is.
Yeah. So those tires are a bit smaller than a car tire, so you get a sense of it. The rocket payloads are typically about 17 inches across, something like that. So it gives a sense of that. So this I believe is probably a test where they're testing the telemetry and the GPS system.
Okay.
So they put it on these trailers, and you can actually just roll it out into the parking lot, and to the right on that picture up the hill there are the telemetry antennas, and they can point them down, and you can turn on the payload, and you can talk back and forth just to make sure your Wi-Fi works on your rocket.
Okay, excellent.
It's kind of a Wi-Fi test, and you hope to get like 4 bars.
All right, yeah, right.
If you don't get 4 bars, it's not very good. And then also make sure that the GPS receivers they have on board are actually tracking and be able to make contact with the satellites. So
excellent.
So this is a fairly common test, and to maintain temperature, they do put blankets around there, and just so that it doesn't cool off very fast.
Right.
So I think we're getting pretty close, maybe to a test rocket, or at least starting the test rocket count.
It's going to be a while.
Okay.
Oh,
No,
we still got a little time on the test rocket.
We still have 3 minutes on the clock, but that hasn't started yet. So
right. And again, as we said earlier, these are not the hot counts.
This is not the hot count. This is just a little test rocket, again, to test some of the systems on the ground and some of the radar tracking capabilities.
Right.
Yeah.
So you might see the countdown pause, change, and that's because these are just kind of ballparks right now. When we get to the hot count, that means when we get to 0, it's going. And again, we're looking at about an hour away from the actual rocket launch. Yeah. So you'll see this time below us change a little bit. We'll let you know when that's the official hot count, and you can set your watch to it. Keeping in mind, again, locally, we're about 30 seconds off. Yeah. So the payload we were just looking at, a little bit over 1,100 pounds in total weight, 4 tons total for the rocket, plus the 2 additional stages. Yeah. And we're going up to about 150 miles. As we talked about yesterday, the space station is about 250 miles up.
That's right.
So this is suborbital, meaning it's coming back down.
It'll come back down, and that's both the altitude and how fast it's going.
Right.
You've got to get to an orbital speed to go in orbit, and this will probably not make that.
Okay. All right.
If it does, we're going to get in big trouble.
That'd be a little problem, right? And so the items in the payload right now, we've got a nocturne camera, a star tracker, and the classic UV spectrograph operating at 250 nanometers.
Nanometers, yeah.
So,
so visible light starts about 350 to 400 nanometers and goes to 700 nanometers. So this is what we call the ultraviolet, which the wavelengths are shorter than what we view in the visible.
Right.
And if you had a light at 250 nanometers next to you in the room, you get a nice suntan.
Oh, okay.
So I don't.
Are you implying I need one, though?
so let's talk a little bit about the spectrograph.
Yeah.
We've got a picture here showing the idea of why we want to look at a spectra. So we've got.
Still got a little radio chatter going on.
Yeah, a little radio chatter. So on the left, we've got a picture showing that if you take a device that can create a spectrum, and the one I think most people know is PRISM.
Yeah, thanks to Pink Floyd.
Among others.
Or maybe elementary school.
or
yeah,
maybe
but
Isaac
right.
Newton.
Okay, whatever. However you know about it.
However you know that. So if you use that and look at the spectrum of the sun, now the spectrum on the bottom is not really the spectrum of the sun, but it gives you an idea. All the colors are more or less the same intensity, right? And it's sort of continuous. So we call that a uniform spectrum.
Okay.
Right. The sun, if you turn on your electric oven and looked at the element inside, it would be warm too. And if you looked at the spectrum, it would be uniform as well. So anything that's sort of glowing and hot is typically that way.
Okay.
Now the aurora is different. If you look at if you took that same prism and looked at the aurora, instead of getting a nice uniform spectrum all the way across, you can see from left to right, you go to red to blue. In the case of the aurora, you see discrete wavelengths.
Right.
And that's because it's kind of like a neon sign. The aurora is caused by electrons coming down and bumping into atoms and molecules. Those atoms and molecules glow in certain wavelengths of light, and those are very discrete. And that's what you see in the picture on the right.
Yeah, and that's why it looks kind of greenish to us, because it's dominated by the green spectrum and not so much by the others.
Right.
Whereas on the left side, I don't know if people are aware of this, but white light is really all colors together.
It's all colors
in equal
together.
levels.
That's right.
And so what we get with the spectrograph is what we call it, a fingerprint or a signature of what's going on in that light, what kind of light it is. And so how can you use that kind of signature to tell what's going on in the atmosphere?
Right, so if we go to the next figure, so again, on the left, I've sort of turned that spectrum around. Now you can see, again, we've got the blue at the top and the red at the bottom. This is another, on the left is the aurora, and again, you see those discrete wavelengths. Again, that 5577 is the green line that we all see in aurora.
Ah, okay.
And
that's degrees Kelvin, then? Or
no, that 557 is the wavelength in the thing called angstroms.
Okay,
so
all right.
We talked about nanometers. We always jump around. We can't be consistent.
It's okay.
So this is aurora when the sky is dark. Now,
right.
When I have that spectrograph running, when maybe there's some twilight, like early in the evening or late in the morning, this is what you look at. And so, first of all, you can see sort of an overall sort of continuous spectrum. Now that's the sunlight again. But what I've noted at the bottom, oxygen has an absorption feature so that when you shine light through it, it actually absorbs some of that light at that specific wavelength. And that's exactly what they're going to do with this rocket, is they're going to run a spectrograph like this, and they're going to look for that absorption feature. But in this case, it won't be O2, it will be nitric oxide, NO.
Okay.
And it'll be at a different wavelength. But the idea is exactly the same.
Right.
And the darker that absorption feature becomes, that means the more nitric oxide the starlight went through.
Right.
And so as they go up in altitude, that dip in that feature, that dip in the spectrum will get darker and darker, or lighter and lighter as they go to higher altitudes.
Okay.
Right.
So the beauty of this is that if you have a light source that's consistent, that you know what it looks like on the spectrograph, then you can use that to detect what that light is passing through, basically by what parts of that signature are missing.
That's exactly right.
Okay, excellent. And so in this case, alginib is our consistent light, and this is a star, what do we say, 4,000 times brighter than the sun?
Right. The absolute magnitude would be 4,000 times brighter than the sun. If you put it next to the sun, it would be very bright.
Right. You're talking about tanning.
Yeah, you get a nice tan pretty fast. Yeah.
Right. And so
and the other thing is, it's also an ultraviolet star. So the spectrum looks different than ours. It would look much bluer. And in fact, there's a lot of ultraviolet light in there as well. And even with our nice ozone layer and lots of atmosphere, that UV would give us a nice tan pretty quick.
Right.
So, a lot of sunscreen.
Okay. Yeah.
Alginib cream.
Yeah, really, exactly. You didn't know this, but maybe you should put on sunscreen at night and wear your sunglasses at night too. Okay, yeah. I'm referencing a lot of pop music tonight, but at any rate, so this alginib is about 333 light years away.
Right.
Okay. So thank goodness it's a ways away from us.
Way away, yeah.
But we have some spectrographs of that star that basically that are that
Right.
become our constant because the spectrographs were taken outside of our atmosphere in the relatively minimal atmosphere of space?
Yeah, so there have been spacecraft measurements of that, and you can even do it from the ground. If you look straight up at the star, you're going through just the very thin layer of the nitric oxide, whereas this rocket would be looking with a long path length through the nitric oxide. So yeah, there are ways to get what the spectrum of the star looks like without the nitric oxide.
Right.
And then when you see that spectral feature, that allows you to figure out how much nitric oxide you look through.
Okay.
Yeah.
So we're going to shoot this rocket up to about 150 miles. That's the apogee.
Apogee is the highest point. Yep.
Right. So before then, Dr. Bailey's going to have about 5 minutes of this beautiful time where the rocket is passing through this nitric oxide.
Yep.
He's pointed at the star, and he's gathering all this data super quickly.
Yeah. So you mentioned the star tracker. The star tracker is what allows the rocket to point very precisely at the star.
Okay.
So they've got I think it's a cold gas system on board that sort of those little puffs to move the payload to look right at that star.
Okay.
And they control it very, very precisely. And then he, in addition to that, he actually has a final little optical stage where he can sort of move and make sure that the star is on the slit of that spectrograph, because you want to know exactly it's going right into the entrance of that thing. And that's what that nocturne camera is about, because he's got a beam splitter in there. He can split off the visible light from the star, look at it with that nocturne camera, and make sure it's lined up with the spectrum.
And all this is happening live.
It all happens in live, real time.
Collecting all these data right away.
The images from that nocturne camera come down in real time, and he has a little joystick. He can actually move that back and forth, and then all the data from the spectrograph are coming down in real time as well.
Right. And the whole thing, door to door, about 8 minutes.
Yeah, on that order, yeah.
So from launch to landing, and then this, is it the nocturne camera that's already been up in space once, or is the telescope part of that?
The telescope and the spectrograph are the ones that have been in
the
space
camera's
before.
been modified from the last
I believe he told me that the camera's been modified, yes.
Okay.
Yeah.
All right. So there's a parachute on the rocket. It's going to land softly. We're going to know ballpark where it is. And then go out and collect that so that he can reuse those instruments.
That's right.
But if for some reason let's just say that they didn't find the rocket, the data is already coming back.
That's right. Yeah, all the rockets we assume that you may not get to go
or you may not get it back in the condition you want.
You plug in the USB port and get the data down. No, you're going to assume it's not going to come back. So we've got several antennas on range that are collecting data from the rocket in real time as it flies, and all that's collected. There's the telemetry building, and that's actually where Dr. Bailey is sitting, because that's where the images will come down directly. And so he gets the information on the images in real time to see what's going on. And they've got multiple recorders down there that are recording the data as it comes in.
Yet another interesting fact, if you are in Alaska and hanging around in the North Slope area and you find a bit of rocket, what is it? $600 for a small piece and $1,200 for a large piece?
Right. Yeah, so if you run across something that looks like a sounding rocket, and you'll probably know what it is if you see it.
Yeah.
Then if you get a good GPS point and get it back to Poker Flat, and we can verify it, we'll send you a check.
Right. Don't try and take it with you. Not that it's going to hurt you, but that it's sharp. You got metal pieces that have been knocked around pretty bad.
Right. Yeah. There's nothing inherently dangerous with other than just it can be heavy and it can be very sharp.
Right. And there's no need to.
Right.
I mean,
we get it.
Let the Poker Flat folks go out and get it.
Those guys
Just take a picture with a good GPS on it, and yeah, you could be good to go.
That guy right over there does it.
Yeah, let's talk to the recovery guy. Sure. Well, actually, let's because we were talking about the sounding rocket. Let's take a break, and if Daniel can pull up this video of to talk more about the sounding rocket, and let's see. This video is by John Hickman, talking about the specific sounding rocket, why it's called a sounding rocket. And we'll play that, and then we'll come back and talk about the whole recovery process, the clean range policy at Poker Flat. So, Daniel, go ahead and roll that video when you're ready.
In general, what the NASA Sounding Rocket Program is all about, the term actually comes from a nautical term for sounding. So when sounding rockets got started, we were basically sounding the atmosphere. We were doing tests with instruments all along the atmosphere. So that's the term sounding rockets. And so what we do primarily is we provide a suborbital flight for our researchers. Suborbital means it just goes up, it comes back down, and our flights can last anywhere from about 5 minutes to about 15 minutes. And in that time, we give the experimenter the access to the space environment to do whatever experiment he wants to do.
You hear me now? Good.
All right, what are we looking at here? What was that, Daniel? Do you know?
This is part of the range.
Okay. Okay, that's where the test rockets are. Peter Elster, you are the recovery lead for Poker Flat here. Thanks so much for coming on.
Sure.
This sounds pretty exciting. So your job is to go out and locate the pieces of rocket that have landed somewhere in basically the North Slope area?
Well, no. South of the North Slope.
Oh, okay. All right. So not that far away.
Yukon Flats.
Okay.
It's between the White Mountains, which are basically just north of the range, and the Brooks Range, which is another 300 miles.
Okay. North. All right. So you, this is not exactly a needle in a haystack because you're tracking the rockets where they land.
That's correct.
As much as possible.
We have, so I believe there are only 3 impacting objects for this mission.
Okay.
The payload itself, the nose cone, and the sustainer, which is the Brant motor.
Okay.
And there is a tracker on the payload, which I'm sure you guys have talked about extensively, Iridium.
No, we haven't talked about it at all, frankly.
Okay. Well, there's an Iridium-based tracker on the payload, and Iridium is just the name of the constellation anyway, I don't know
enough
about
it to actually talk about it.
Iridium is a brand name.
Okay, all right. Is it just like a GPS type thing?
Yeah.
Okay, all right.
It's like, you familiar with Garmin InReach or Spot Tracker?
Sure, yep.
They use the GPS constellation to localize your position and send it to all your friends and family.
Right, okay.
So that's, and there's also an Iridium tracker on this particular mission on the motor, which is a new, fairly new technology.
Okay.
The motors come in from space, and when they separate from the payload, they maintain, because there's not a additional sustainer like on some of the larger rockets. So at the final separation point, they kind of maintain a similar trajectory. So they usually end up in the same place.
Okay.
And in the past, we've relied on just going out and looking for kind of a dark stain in the snow.
Got it.
To find the motor.
Okay.
Obviously, the payload, if the Iridium is functioning, is very easy to find.
Good.
You can get within a few meters.
Excellent.
And there's a giant orange and white parachute.
Right.
Obviously, usually hanging in a tree.
Okay. Right.
Small. It's usually tangled in something.
Right.
And then
and a bear's gnawing on it and something like that. Well, not this time of year yet.
No, I haven't seen that yet. Maybe for the April launches if we do those. And then, so the motor, so the payload's going to come in, and it's not, you guys were talking about like the unpleasant trip up and back for a sentient being, and the payload doesn't come down like a guy in a parachute and comes down at the last minute and
right beautiful
lands beautifully.
Yeah.
It just thuds in the ground.
Okay.
There's actually a crush bumper at the bottom of the payload to take up the impact.
Okay.
And then but that's still a pretty soft landing.
Okay.
We have some statistics that indicate that the motors often are supersonic until just before impact.
Really?
And sometimes impact Wow. Supersonic.
Oh
So,
my goodness.
So this,
which is 700 some miles an hour.
Around there, yeah.
Yeah. Okay.
So the is very dependent on just the dynamics of reentry, which are, I don't think, very well understood for these rockets because it frankly doesn't matter. So
that's a great way to say. I don't need to understand that because it doesn't matter.
Yeah, I mean
that sounds like pretty much all of high school for me. Turned out it did matter, but anyway. Right. Okay.
Well, you're on TV, so it's okay.
We're on YouTube. It's not.
Not quite the same.
We'll edit this out, right? This isn't live. Anyway.
So anyway, this is.
It is live, by the way. That was a joke.
This is all to say that the little tracker that they've developed to put on the motors, they've moved it all the way to the back. So when the first 15 feet of the motor buries itself in the ground, it won't be destroyed.
Okay.
So it's right in front of the fins. It's strapped on with these huge bands, and it's basically a iridium about the size of your thumbnail.
Okay.
But it doesn't actually turn on until it hits the ground.
So it knows when it hits the ground a bit.
So,
but it's going into the ground a bit, isn't it?
It does, but the idea is that usually the fins and the very back part of the motor survive.
Okay.
And so as long as it can survive whatever the impact G's are, then it should.
All right.
It's been successful on payloads, but
okay.
I believe this is the first time it's being tried on a motor. So.
All right. Excellent. Peter Elster, recovery lead.
Yep.
Good luck.
Thank you.
Tracking all this down.
Yeah.
And keeping up with that clean range policy that you all have here. So, all right, we've got another video that I want to show, and this one is about the folks who are working down in the telemetry building houses, and I don't know, Daniel, if you got this, but here's some other folks who are involved in the mission here tonight, helping to figure out where this stuff is going, right? Basically.
Yeah.
More or less.
Sure.
Whatever. It'd be convenient if you said that's correct.
That is correct.
So let's roll that.
There are several key positions that are required to support a sounding rocket launch out of Poker Flat. We always have a campaign manager. He sort of runs the operations from the NASA perspective, making sure that everything's run and kept on time, solving problems, issues, all those things that come up. Additionally, we'll have a range safety officer there, which will have safety support underneath him, an operational safety supervisor and a wind waiter. But he's the one that actually gives us the go call based on winds and safety and clear space, surveillance, those kind of things. Additionally, we'll have a launch officer. That individual is actually the one that pushes the button at T0 and does all the checks and stuff and actually operates the launcher in azimuth and elevation. So he basically points it where we need to point it and fires it when it's time to fire it. Additionally, we have a mission manager who oversees the entire sounding rocket team, which would consist of motor, telemetry, attitude control systems, all those technicians. With the range, we have range asset personnel which control all the telemetry antennas, the radar, and that's probably around 20 people to actually track the rocket and also receive all the data that comes from it while it's flying. The team coming up to support Bailey's launch will be approximately about 35 people.
All right, and we're back. I'm Red Shirt Guy, and you're Plaid Shirt Guy.
Plaid Shirt Guy.
This is in reference to some lovely comments we're getting online. These are very flattering.
Okay.
Arnaud Muller says, well, that's not what I meant to say. No, he says, Red Shirt Guy, can you host SpaceX streams as well, please? From your lips to God's ears. I would love to do that. Thank you for not being too irritated by my lack of knowledge. But I consider my ignorance to be an asset when it comes to things like this, because you never have to worry that I know more than you about what's going on. I will always be the least informed person in the audience. So any question you might have, I will have 5 layers before I get to that question. And so the latest question right now is, what's the status of the test rockets? Daniel, you want to have a... I'm not asking you if you know. He's giving me I don't know. I know you don't know, but can you show us a shot of the test rockets here? So we've got that. going
so
on.
You can see our rocket, the big rocket on the right.
Okay,
right?
excellent.
Off to the left where the light is there, I think that's the pad 1 where the test rocket would be.
Right.
So,
and I have a little tip for you. If you ever see a light that's going around in a circle like that, you want to go the other direction.
That's right.
Because that light means there's some serious fire and blasting that's going to be happening in a little bit.
That's right. Anywhere on range, if you see a flashing yellow light, it's probably a good thing to stop or go the other way.
Yeah, I just imagine some poor Alaskan out, wandering through the woods, and all of a sudden comes across this spinning light. Like, follow your tracks back, because that light means business. So we got some test rockets that at some point we're going to go here.
The technicians are still on pad 1 working on loading them up and getting them ready.
Okay, so we're loading those up, getting them ready. We're about 40 minutes away from the estimate of when we might launch this polar nitric oxide or polar NOx mission. And so, but again, that's a ballpark. So if you're tuned in here, that gives you a little sense of how long before we're going to go. We don't have a countdown for that right now. And so again, these little rockets, what happens to them? Do they have little parachutes?
They don't have little parachutes.
You have to have a moment of silence for the little rockets.
Oh yeah, their time is a little bit limited. Yes, but no, they basically go across the highway and land on again university property over there. It's a ecological research site. And yeah, that's where they go.
Right. And so the idea with these is to test the launching system?
The launch system on the ground, and then it's some time to test the tracking radars.
Got it.
There's no telemetry on board. They're just little rockets. They don't send out any kind of pings.
Right. Okay.
And the test rocket, they can also look a little bit at winds on the first part too. So.
All right. Excellent. So we'll let you know when we're getting to a countdown to do those.
Yeah.
Is it possible they won't do those tonight too? Or, I mean, is it
it sounds like they're on their way, so it's very likely they will.
Okay.
I think if it starts impeding the actual main rocket, they might think about it. But I don't want to second guess what they're going to do. So
right. Okay.
So that's I think they're I think they're in the process of doing the test rockets. So I think they'll get it done. I can maybe see some activity over there. So
okay. And now as I pulled into the building this evening, I was walking in, I couldn't help but notice a giant laser pointed up into the sky.
That's right.
It was kind of mesmerizing.
It's pretty cool to look.
With some of the steam and fog going through it.
Yeah.
Everything about Poker Flats. I mean, I still can't get over the fact that I drive up to the gate and like a voice talks to me. Was that you, Dave, that was talking to me? I wasn't sure if I needed to say who I was with or anything. Yesterday when I pulled in, Linda was like, just go up to the gate and talk. And I was like, I don't want to get shot.
No.
I was assured I wouldn't get shot, but now I know Dave better. I don't know so sure. But there's a lot of just fascinating things going on here.
Right.
What's the deal with this green laser?
The green laser. Well, that's a system called a LiDAR.
Okay.
So
which stands for something about radar.
Yeah. Well, no, it's light detection and ranging.
Oh, okay.
Right.
All right.
Versus radio detection and ranging.
Oh,
which is
right.
what radar is, right? So, but it's the same principle. In radar, you send out a radio pulse, right? And it reflects off something and comes back. And if you measure how long it takes for it to reflect back, you can say how far away that thing is, right?
Okay.
So the same thing with the. Oh, here we got an announcement.
Okay. Ooh, 3 minutes and counting.
3 minutes. So,
excellent.
Right.
All right.
So, there's a graphic on the screen right now.
All right. That's the 3 minute mark.
Starting at 3 minutes. So
okay.
So I'll talk fast.
And well, it's just again, this is the test rocket.
This is just the test rocket.
The main rocket.
Yeah,
so you won't see this anywhere unless you're
here on the range.
Chattanooga Lodge, maybe. I don't know.
Or here on the range, and it lasts for about half a second, and it's gone. So
okay. But anyway, so we're talking about the LiDAR.
Yeah. So basically, you take a pulsed laser, puts out very short pulses. You know when it sends out the pulses. And then you've got a large telescope that can look up that beam. It looks like a beam, but it's actually a series of pulses going up there.
Oh.
You've got a telescope looking up that direction of that beam, and it has a very precise timer on it. and it looks at the reflected light from that beam or that pulse of light that goes up, and if it runs into more dust or atmospheric scattering, you get a brighter signal coming back, and if it runs into less dust, you get a smaller signal coming back.
Okay.
And so they put a time series together, and they can figure out at what altitude you've got dust or you've got a species that this specific radar can reflect off of.
Okay. Now, let's say a raven were to fly by right over this laser. What would that raven experience as it passes? Is the laser pass over it?
The raven itself would be fine, unless it happened to be looking down at it. The light is very bright, and it would burn out your retina.
Okay,
but
all right.
it won't cut any. You couldn't cut metal with this laser.
It.
Yeah. It is very powerful, but it's the beam itself is about an inch and a half across, and so the density is not that very high.
We were talking earlier, it will pop bubbles.
It does pop bubbles.
So if you're a bubble, you do not want to float over this.
Yeah, and I wouldn't recommend putting my hand in the beam.
Okay.
But
you should have told me that beforehand. That was the first thing I did.
You did, yeah.
Laser.
Right.
Let's put my hand in it. Okay, where are we at in the countdown for the test rockets here?
Right. We're about a little less than a minute. Okay.
Just under a minute. This is test rocket.
Test rocket. This is
little
not.
rockets.
This is not polar Knox.
Don't go outside. Dan, you want to get a shot of the range for us again? And as we count down to the test rockets, just as something fun to do.
There we go.
Okay.
See a quick little flash.
Yeah, it's a little bit of a flash there, and
it'll be a quick flash.
It'll be out of the field of view in less than a second.
All right, but it's something to look at besides red shirt guy and fly guy for a little while.
Red shirt guy.
All right, so we'll listen here for the countdown to the test rockets. Little rockets, couple feet.
Yeah, about 2.5, 3 feet long.
All right. Oh, hearing people running in the hallway.
Yeah. It's a good thing to watch on range.
Okay.
Okay.
I'll stay to my post here. Here we go.
5, 4, 3, 2, 1, 0, +1, 2.
All right. Hey, that's pretty good.
Yeah. And you just heard the announcement that the radar is tracking it. So this is one test they do is the radar, the tracking radars for the big rocket will practice on this one. That's part of the testing. Yep.
There you go.
Yeah.
So you got to see a rocket launch tonight. Don't complain. if we don't get to do the big one, we got to do
something.
Right.
There will be a second one.
Oh, there's going to be a second one.
They typically do.
Do we know at what time? Let's go back to that shot, Daniel, if we can. And do we know at what time we're
they'll usually they'll rotate around at about a minute or so.
Okay.
You know. They'll wait a minute and then they'll.
So we're not closing the road or anything.
No, the road's closed.
Oh, it is.
No, the road's definitely closed.
Okay.
Yeah.
All right. And this is another one airplane. We're watching out for airplane.
Absolutely. No. All the same safety things.
Oh, okay.
All the same safety things for the
Even
big
NORAD?
rocket.
NORAD doesn't.
NORAD probably didn't really care, but we certainly talked to FAA and they let NORAD know. It's very unlikely that anybody else's radar would catch this. Although we have U.S. radars that might be catching it as well. So.
Okay, excellent.
Nope.
Okay, just the one. All right.
Very often they do too, but I guess tonight they
saving it for
4th
of July.
That's right.
All right. But it sounds like everything went as planned. I haven't heard any.
Well,
they're tracking it.
The main thing that would be over the radio would be that they're tracking it with the radar.
Right.
And that's a big test because we want to make sure that radar's working. Okay.
All right. So you just heard we're at 30 minutes. This is not the hot time.
Well, so if they're 30 minutes and counting, that could go hot. They'll let us know as they get closer.
All right. Yeah. So again, this number it's a good point of reference.
Good point of reference.
Like if you're planning on, I don't know, if you got some laundry you're doing.
Yeah, if you want to watch Game of Thrones, a season of Game of Thrones, and I'd start just half of it.
Right. So this is not for sure yet, but this is what we're generally thinking is going to be the launch time for tonight. Pretty exciting. Again, yesterday we got to 0. Unfortunately, weren't able to launch the rocket. So tonight things are looking really good. I haven't heard any hiccups at this point.
And I'm sure they tested what the issue was yesterday, and I think what we can say is it was not a problem with the rocket itself. It was probably something with the launch system itself. And so given that we're counting again, that they would probably fix that. Yes.
Right. Yeah, which is excellent because getting a spare rocket up here would be a challenge.
If Amazon, maybe 2 or 3 days. Yeah.
You know what it would be. For anyone who lives in Alaska, you're like, I want that. That's great. And then you go click on it. It says does not ship.
Deliver. Yeah, right.
You're like, oh, why can't
I think pretty much any Terrier Mark 70, any place in the United States would probably say that for Amazon.
Which I think, let's talk a little bit about Poker Flat. This is the only university-owned rocket range in, well, I like to say the universe. That's because I don't believe in the infinite universe.
I'm not sure I can go that far, but we can certainly say on Earth.
I think we can safely say on Earth.
Safely say on Earth.
As for if it's the only one in the universe is yet to be determined.
Well.
But so what does that mean in terms of our relationship with NASA, with the military? I mean, if we're the only university-based rocket range, how do we work with these organizations to get these rockets, to cut through or meet all the requirements for the government to say, okay, here's a missile.
Right.
UAF. Do good work with it.
Well, we own the rocket range. We contract with NASA, and they bring the rockets and their team up to actually launch them. So they take care of the preponderance of the paperwork that goes along with getting the rockets here and making sure that they're safe as they ship up here. Once they get here, a combination of Poker Flat personnel and NASA personnel handle the rockets and get them ready to go. We can talk about the whole process to get one of these rockets to this point. So somebody like Dr. Bailey or even people at UAF and other places have an idea of what they want to do. Dr. Bailey says, well, I want to look at nitrous oxide in the polar night.
Right, and just for a moment here, I want to step back. So Dr. Bailey, he's researching this, but he also just knows how to launch rockets?
No, he doesn't launch the rockets himself. He knows enough about rockets to know what their capabilities are.
Right. So what he's busy with right now is making sure that the payload is full all that. But NASA folks are the ones who are working on making sure that the rocket's operating.
That's correct.
And doing countdown and pushing the button.
Right.
Okay, all right,
great. So Dr. Bailey wrote a proposal about 4 years ago to NASA and said, I have this idea. I want to look at nitrous oxide in the nitric oxide, excuse me, in the polar night, and said, here's how I do it. I build a telescope with spectrograph, yada, 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 and go to NASA and say, I need to go to this altitude, and they would say, yeah, we can do that with this combination of rockets.
Right.
And so they go through, there's actually a competition with a lot of other people, and so you get selected, and they start the process when they get the money, and they start building this, and about 2 to 3 years later, they take it to Wallops, and they test it first.
They test what? The
well,
rocket?
They test the rocket and the payload.
How can you test the rocket?
Well, you do weight and balance on the rocket to make sure you know how heavy it is and how it's going to perform.
But you don't light the end.
You don't light the end. No, you don't send it off and say, well, it worked.
Exactly. Yeah.
There we go. Here's
excellent.
a picture.
So is that Wallops then?
That's a test site at Wallops.
Excellent.
So the main thing they test at Wallops is that the payload is going to survive the launch environment. Now we talked about the very strong shock during launch.
Yep, 10 Gs.
10 or more Gs, and then as it's flying, that rocket motor is not a smooth ride. It's not like your Lamborghini.
Yeah.
It's not like
yesterday you were referencing my Rolls Royce. I have a DeLorean in real world. How can we never mention that? You always make up these other cars. You never, because if you give me an opening, I'll never stop talking about it.
I want to keep talking.
Like, forget the launch. Did you hear I have a DeLorean? Right.
So it's a very rough ride.
So it's like a pow.
Bam, and then it shakes as it's going up.
Right.
Very, very badly. So a delicate telescope like that, you want to make sure it's going to survive that. So they've got tables at Wallops. They can't do the bang, but they can certainly do the shaking back and forth to make sure everything's going to survive that.
It reminds me of that experiment in middle school where you drop an egg off the second floor building.
That's right.
But I assume they're not using like toilet paper and egg
No,
cartons.
no.
Something more sophisticated. But that is pretty amazing that this delicate technology can take 10 Gs.
That's right, yeah. So
survive it. And it's not only survived it once, it's survived the launch, the time and space, the landing.
Right, and they're doing it again.
It survived Peter running out there and throwing in the back of a helicopter, coming back here, and now it's launching again.
Yeah.
That's pretty amazing.
Yeah. So that's.
You talk about Amazon, I'd give that a 5-star.
Okay, that's good.
I got a lot of like Bluetooth headphones that can't handle a 20-minute jog. This is pretty impressive.
Yeah.
What this telescope has gone through.
They do cost a little bit more than your headphones.
That's true. That's the problem. I always go for
the cheap telescope. That explains part of the cost for some of these missions. That you've got to survive this in order to get to space. So.
All right.
So then from Wallops it gets up here.
By truck. We talked about yesterday.
Yeah, it comes by truck. And then they basically reassemble it all here.
Which we talked a bit about how we have an arrangement with Canada. But I cannot imagine pulling up to the border in North Dakota or wherever it comes in and be like, what's in the back? A missile. I'm terrified at the border that I might have forgotten, like, oh, maybe I have some rounds of 22 in there that I forgot. That they're going to be like, head back, Slinger, you're going back to Fairbanks.
Right.
You have a missile in the back.
Right.
I want to be there for that moment. Can we arrange that?
It would be fun to be a fly on the wall.
It would be.
And hear the conversation. Yeah, what do you got in there? Yeah. Well, here's the paperwork. You take a look.
In my experience with Canadian border crossing, they pick the most jaded, angry 20-something-year-olds they can find. They scour Canada for the grumpiest 20-year-olds, and those are the folks they put on the border.
Are you trying to start an incident? Are you trying to start an incident with Canada?
International incident with Canada. Come on, Canada. I dare you. I love you, Canada. I'm kidding. Anyway, so it comes up by truck, and it pulls in here, and then you all have various facilities where you keep the rockets?
Yeah, we got a storage facility that's specifically designed for storing the rockets, and then a couple of places where they do what they call rocket assembly. So it doesn't come with the fins on there. They've got to put the fins together. They put the igniters in and other things like that. And then when everything's ready to go, they roll it over to the launch area. Usually they put on the first stage. That's a good thing. And they put on the second stage, and they put the payload on. Sometimes they try the opposite direction. Didn't work very well. No, sorry. We've got some pictures going, and this is the payload itself for some of the testing.
Oh, is that Dave out there earning his money?
That's right. No, I don't think so.
No? Oh, it's not. Okay. That's above his pay grade, is to be out there serving as the push cart driver. But
you've got these carts, and so we roll them around the range on the carts, and then they've got special apparatus to put them onto the launcher, and then bolt them together. And then, as we talked about yesterday, you want to maintain temperature, not even just for the motors themselves, but also for the payloads. The payloads can be fairly delicate and don't want to see large temperature swings or get very cold because they may not be designed for that.
Right.
So what they do is they build a big styrofoam box around the whole contraption. They've got a few doors there for access to the payload and things like that.
Yeah, what I like to say is it looks like the most obviously wrapped Christmas present.
That's right.
Christmas morning, you come out there and you're like, I don't think that's a DVD. I think I got a Terrier Mark 70 and a Black Brant 9 again for Christmas this year.
And I get that every year. It's really bad. I wish I got some socks or something like that.
Right. So anyway, that's what it looks like on the launch pad. So when we go to the shot of it on the launch pad eventually, I'm not sure.
It looks similar to that. This may not be the same one, but
it may not. It may not. Yeah, I mean, this is pretty good. It may not meet your expectations for what a rocket on the pad looks like.
And you saw that yellow hose going in there. That's basically a portable heater, and they're piping in warm air to maintain nominally room temperature. They've got a temperature range they have to maintain, and they've got sensors on board to confirm that they're maintaining that, and people will watch that. There's a actual job out here called Heater Watch.
Oh, fun.
And the job is to watch those heaters to make sure that the rocket maintains temperature.
Right.
Yeah.
Another person in Alaska making more money than me, I'm sure. Daniel, thanks, A, for your job here switching. You're doing a great job. Daniel's our director this evening, who's making sure we got the right stuff on screen at the right time.
Right.
So with all these challenges here, we said it at the beginning of the live feed, and again, we get a lot of questions on YouTube. When are we going to launch? When are we going to launch? We're looking at about 20 minutes from now.
Yeah.
So it's currently 4:20 Alaska time. We're looking at launching about 4:40-ish.
Right.
Which ish I came up with was the acronym yesterday for what? Remember, what does ISH stand for when it comes to timing?
Yeah,
you said something
in.
It worked yesterday.
It
I
worked
was so
yesterday,
proud of it. You were like not very impressed with the fact that it spelled out ish. But
I'm always impressed with you, Rob.
Yeah. You could show it more.
Okay.
In non-verbally. Anyway, so we got a lot. We got to wrap this thing in styrofoam. We got to ship it all the way up through Canada. It's got to endure. It's right now. Last time we checked, it was about 24 below.
Right.
Why are we doing this here rather than you were telling me yesterday about this beautiful island where you're on? Where you were launching rockets, where the only downside was the island was small and you could only get so far away from the rocket. You're all like standing with your up to your knees in the ocean to try and be on the other side of the island for this thing.
Right.
So one advantage is there's not a lot of people up here.
Yeah.
The range where it's going to land, not a lot of people.
Right.
Why, other than the beautiful landscape, why are we launching this rocket and other rockets from Poker Flat here, which is about an hour north of Fairbanks in the golden heart of Alaska?
Well, I mean, the original point was we wanted to understand what the aurora was doing, right? So
not a lot of aurora around the equator.
I mean,
it concentrates around the poles.
That's right. It's around the poles.
So if you think Fairbanks is unpleasant, try Antarctica.
Yeah, right.
A little harder to get
a little hard to get there.
there.
They tried the truck a couple of times. It just didn't make it. No. The idea was in the late 50s, early 60s, there was quite a bit of interest in what the aurora was doing, especially to communications. And as some of these rockets became available, people had the idea that maybe we could use them for doing scientific research. So Neil Davis, who is the namesake of this building, had the idea that, hey, we know some places where there are not a lot of people. There are people, but there are not a lot of people. And we're close to the aurora, so why don't we set up a range that we could start doing that? So in 1969, they had sometime in March, they had their first rocket launch. Then it's been going ever since. So we're a little over 50 years now.
Yeah, which, as we said, pretty amazing a few months before the moon landing.
That's right. So the idea is this is a way to study aurora before we had sort of systematic satellite missions to do that as well. But we still do the rocket launches because you can time them very precisely for when the aurora is going over. If you had a satellite mission that's going into polar orbit, it goes up by every 90 minutes or so. And so that's longer than a typical sort of cycle for what we call a substorm, which is the activation of really active aurora. So you could have a substorm and the satellite wouldn't even be there.
Right.
Whereas if you're sitting here watching on the ground, you can send a rocket up and fly right through the aurora that you want to fly through. Yeah.
Yep, and we were talking yesterday about how this is a relatively low-cost way.
That's right.
What's NASA's acronym or reference to?
Low-cost access to space.
Low-cost access
LCAS.
to
Oh, yeah,
space.
we know that word around here very well.
Right, and low-cost meaning $1 million to $2 million.
Yeah, million-ish kind of dollars is a typical science team cost, and there's also cost to Wallops, but it's part of a larger contract. But that's compared to even a fairly small satellite mission costs several tens of millions of dollars. Right.
Yeah.
Like you say, we get about 5 minutes worth of data, but you can really tailor that data.
Yeah.
You get months of a satellite mission, but you may only cross the aurora that you want 2 or 3 times.
Got it.
Yeah, so.
All right. Do we have any updates here on our progress? All right. So I'm not sure you can hear Linda off camera here, but we're talking to Linda.
Somebody wants to hear a little bit about range instrumentation, the radar telemetry, those kind of things. And then another person is asking, again, what the rocket hopes to observe. So maybe if we could just play that video, work that video back in
before
the launch.
Yeah.
So why don't you repeat the questions? What was the range? What's the first question?
The range
right instrumentation on the range.
All right. So talk about the instrumentation on the range, and then we'll go back to playing a video about our mission tonight. This is the Polar NOx mission. Basically, quickly speaking, we're measuring nitric oxide in the atmosphere in space.
Right. And so instrumentation on range. There are devices that are going to be contacted or be in contact with the rocket as it flies. So those are some telemetry antennas that are basically, I mean, essentially Wi-Fi connections to the space, the rocket.
Okay.
It's different than that, but it's nominally the same. And so they are sending commands to turn things on, to operate the instrument. But they've also downlinking the data that the instrument's producing in real time.
Okay.
We've also got tracking radars, which are just following where the rocket's going, so we know where it is all the time. And as Peter talked about, we use that as sort of the first guess of where the rocket parts may have come down, and then there's also onboard things through that as well. We've also got, at the range, we also have all-sky cameras. We've got a very powerful radar that can look at the ionosphere. We've got magnetometers looking at the aurora. Those are not as important for this launch, although they're very important for ones where we're targeting aurora specifically. And those are running all the time. They're not just specifically here for rocket flights. We run them even when the rockets are not going, because that gives us a long-term data set of what the aurora does over the years.
Okay.
But in this case, and we're going to get this video in just a second, we're looking at sort of the long-term effects of aurora in producing nitric oxide and how that evolves and transmits or transports around in the upper atmosphere. So
and how it interacts with the sort of the relevant application of this for us is that the ozone layer is the reason we can survive on Earth.
It's part of the reason we can.
Right. I mean, okay, other things, water, and Netflix and stuff, but
but
otherwise, yeah, exactly. So, so it's very important to us what's happening to the ozone layer, and we're trying to figure out how this nitric oxide is interacting with the ozone and how it relates to the aurora.
Right. So in this case, it's the aurora is a production source for nitric oxide, and in sunlight, the nitric oxide would go away, but we're in the polar night, so we get very short amounts of sunlight.
Right.
And so it actually is a long-lived species here, and so it can actually migrate from the altitude where it's produced in aurora up at 110 kilometers or about 60 miles up, down into the stratosphere where the ozone layer happens to be. And there have been some cases where they've seen that effect, and so we need to understand that a little bit better so we can understand when that might be when the ozone might be in trouble.
Okay.
So,
all right.
We'll take a look at what.
So we've got this video here with Dr. Scott Bailey. He's the principal investigator for tonight's research. He's from Virginia Tech, along with Dr. Justin Karstens, who's the co-investigator from Virginia Tech. So let's roll that video. Again, this is a ballpark countdown we've got going on here. We're not in the hot countdown yet, but are we in hot countdown?
We're getting close, I think so.
We're getting close to it. So you could pretty much figure this, but minus 30 seconds for those of you who are in town here watching. So, Daniel, we have that video ready to go?
We're trying to measure a chemical, nitric oxide, that's created by the aurora and grows to large abundances in the polar night. We want to see how much there is and where it is, where in altitude. What's really interesting about this is we've measured nitric oxide all over the globe, but we usually measure it using techniques that involve sunlight. And nitric oxide is created by sunlight. It's also destroyed by sunlight. But interestingly, it's created by the aurora as well, and the aurora occurs in darkness. And at high latitudes, you have the long polar winter. And because we're using starlight, the way we would normally use sunlight in the rest of the Earth's atmosphere, we're using starlight as the light bulb. We need a star to be in exactly the right geometry. It needs to be in exactly the right place.
We'll be using algeneb on this mission. We're using that star because it's bright in the UV, and we need a UV light source. The payload has a UV spectrograph, which it measures light, UV light, at this particular color we need that is absorbed by nitric oxide. So we'll be looking at the star. It'll be filtered through the atmosphere, and nitric oxide will absorb a lot of that starlight, and how much of that starlight, the color it absorbs at. That'll tell us how much of it's between us and the star, so how much is in the atmosphere.
But there's a lot of physics between the creation of the NO and the destruction of ozone that we just don't understand. So measuring the nitric oxide, measuring the altitude profile is going to help us understand that, and that's what we're after.
Should we have the spectrograph back?
All right, and we're about 10 minutes away. We're not, which is, people can pretty much bank on that at that point.
Well, they're going to go through the checks as they go into that into the launch countdown. But yeah, we're looking quite good now. So
right, and I'm seeing some chatter on the YouTube page. Thank you, Jason, for saying you got about 28 seconds of lag on the stream here.
Okay.
That means that if you are local, what you're hearing right now is 28 seconds in the past.
TM check 188.
Right.
Which
so don't count on going out at 0.
So as we said earlier, this is not New Year's Eve. Do not wait until the 10-second countdown to go outside. I know it's cold out, but about T-5 here, so about 5 minutes you're going to want to go outside. And let's see, what other, we have some other questions here. So, you know, just to kind of clarify, there's the question of, are we measuring starlight? In a way, we are, but we're not. We're measuring starlight because we want to get that spectrograph to see what we're actually. I mean, measuring the nitric oxide in the atmosphere.
That's right.
At
yeah,
how far? You said about 60 miles up. Is what levels are we looking at the nitric oxide?
The nitric oxide, yeah, from about 40 miles up to about 80 miles, something.
Okay.
Like that. Yeah, they'll be measuring over that range. Yeah, we're using the star as a known source. So we're measuring the starlight, but we're measuring how the nitric oxide is absorbing that starlight. And the more it absorbs, the more nitric oxide there is between you and that star, which is here in our atmosphere.
Right. Excellent.
Yeah.
And so I don't know if we want to try and bring Alex back in here really quick. We've got about 5 minutes to go. Is it it's too tight?
That's
all right.
A little tight.
So let's if maybe after lunch we can bring you in here a minute. But I do at some point want to get Dr. C. Alex Young on here as well. He's the Associate Director for Science in the Heliophysics Division of NASA's Goddard Space Flight Center, who is up here for this as well. And it's been a pleasure getting to know him a bit over the last few days. And he's got a lecture coming up Tuesday night at 7 p.m. in Raven Landing in Fairbanks. And that's about basically solar weather and
space weather.
Space weather,
right?
Yeah. So we can talk with him a little bit after lunch here. But we're what do we got going on? You want to go back to the countdown? Take a shot at me here, Daniel.
There you go. Yeah.
Daniel, former student of mine.
7 minutes.
Doing a great job here. We got 7 minutes. Do we know is this hot yet?
Oh, yeah, we're hot.
Okay, we're hot.
We're definitely hot.
So
we're
you
going
can
through the countdown.
That means you can bank on this. Up until before we were hot, it was a ballpark. When we're exactly where we're going to go, the countdown was more of a guideline than a rule.
Yeah.
And now this is it. So in a couple minutes here, I'm going to bail outside too, because even though I am a dedicated color commentator for tonight's rocket, I have never seen a rocket launch. This is my first rocket launch, so I'm going to leave you all in the capable hands of my colleague here, Dr. Don Hampton, who will be talking you through the launch, because this is not your first time around.
No, I've seen a few.
You've seen a few of them. So he can keep you informed on what's going on and the details behind that. What kind of things are going on here as we get to the last 5 minutes? What sort of things are they talking about and doing?
So again, they're going through their checklist, and they're looking at voltages, they're looking at temperatures, they're looking at communications with telemetry on the ground, just to make sure that everything is still operating correctly, because there's no reason to launch this rocket if there's something not working correctly.
Okay.
At some point, they actually switch over from external power to internal power. They've got batteries on board. Again, that's a transition they want to make sure works before they'll let the rocket launch. So this is the time you're talking to FAA, you're talking to NORAD, you're looking at your weather, or your not your weather radar, you're looking at your aircraft radar to make sure there's nobody coming in. So it's just basically all the things that they did during the test, but it's just a little bit more important that they do them right this time.
Right.
So,
okay.
Yeah. So yeah, it's you'll hear some chatter and you'll hear check items so and so, and that's the checklist as it goes along, just to make sure that everything is working as we expect on the rocket.
Right.
Yeah.
And again, I'm sorry if you've heard this a million times tonight, but I just want to be absolutely sure. Folks who are watching here in the interior who want to step outside and see the launch, you want to head outside right about now.
Pretty soon.
This is the good time to go outside, and you can see this from Fairbanks.
Fairbanks,
We got folks in North Pole.
Yeah, if you look to the north, and you get a pretty good view. If you've got a big hill in the north, in North Pole, you might not be able to see it. But pretty much anywhere in Fairbanks, you'll probably be able to see the second stage, certainly.
Right. And so we're going to show video of the launch, of course, but it's going to basically go from rocket on the pad to flash of white to gone. Because this is an extreme, for video technology, this is an extremely difficult thing to capture the change.
You go from nighttime to pretty much daylight.
Yeah, right. And then we're going to cut to the all sky camera.
We'll go to the all sky camera.
Like a 360 fisheye lens.
It's a big fisheye lens, so and you'll see a little bit of a streak going through that. And so you should see the transition from the first stage to the second stage in there at some point.
Right. And I'm going to wait on Linda to tell me when I should jump out. Now's the time? Okay. All right. So hey, everybody, it's been a pleasure. I'll be back in a minute. I'm going to run outside because I'm excited to see this myself. Don, good luck.
Okay. Well, good luck to you.
All right. Talking to yourself.
Stay warm out there.
Thanks a lot. It's exciting.
Right. So we're about a little less than 4 minutes away. They're still doing the checks on the checklist. So again, this is in preparation for the PolarNox launch. Scott Bailey for Virginia Tech is the principal investigator. This is a NASA sounding rocket to look at nitric oxide in the polar atmosphere. You see a picture of the rocket there, again encased in its styrofoam. They've got it pointing in the direction they expect to launch. Chatter's pretty quiet right now. Everybody's just working through their checklist now.
3 minutes.
You just heard we've got 3 minutes now. Again, I will say that if you're watching this locally and you want to watch the rocket live with your own eyes, it's probably a good time to be going outside now because this YouTube stream is often delayed by as much as a minute. It sounds like we've got about a 30-second delay right now, but don't count on that. Get outside now and look off to your north. If you can't see the first stage, you should certainly see the second stage go off.
TM check 212 and 215.
RCV check 217 and 224.
Telemetry and the NASA crew are checking off items to make sure all the parts are working. You can see some steam out there. That's probably from one of the portable generators that's maintaining the temperature on the rocket itself.
TM check 221 and 223.
2 minutes.
Now it's the 2-minute countdown. So again, if you're local, you should be outside by now.
Check 222.
Again, this is a 2-stage rocket. We'll see the bright flash from the first stage here and hopefully see the second stage in the all-sky camera. Poker's down kind of a little bit of a valley, so unless you're local, you may not be able to see the first stage remotely, but you should be able to see the second stage, which has a bit longer burn and will already be up at a couple of miles out.
RCV, go.
RDT.
Go.
Doing final checks of all the major subsystems.
Go.
Radar.
Go.
PLC. F. FC.
FC's go.
Surveillance is go. PC.
Go.
ACS. LO.
LO, go.
So about a minute away from the launch of the PolarNox sounding rocket.
VS.
VS, go.
60 seconds. CM.
CM is
go. Rocket should go to about 150 miles
Range is go.
at apogee.
40. 30.
ACS, check 228.
20. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3, 4, 5, 6, 7, 8,
Our first
9,
stage
10.
is now burned out. We should get a second stage.
Radar tracking.
We just now heard the boom here up at the range.
Second stage ignition.
And we've got confirmation of second stage ignition.
Plus 30. Plus 40. Plus 50. Plus 1 minute.
So I think what we're looking at now is probably a star in the camera.
Motor set.
No, I think we're tracking it.
Shutter door.
Yeah, you have.
Okay.
We have data. I'm swapping the measurement mode back for you.
Okay, we're getting confirmation over the headset that they're tracking the radar, or tracking the payload and getting telemetry.
Copy.
You can see a picture now of the launch pad, which is now empty of rocket because the rocket's on its way on about an 8-minute flight up to about 150 miles apogee. So as the second stage is burned out, now they're able to start pointing the payload at the star they want to observe. And we just heard that the telemetry is actually coming down. They're getting telemetry at the telemetry site.
Excellent.
They're swapping over modes and going. So
okay.
We won't hear a lot more information. They'll be pretty busy making sure that they've got it pointed correctly and are getting in the right direction.
Right. So we're about 2.5 minutes in.
Mm-hmm.
So about a third of the way through the duration of this flight.
Yep, that's right.
When does Peter have to go out and collect this stuff?
So he will be heading out potentially tomorrow.
Right.
They have some paperwork they have to do in order to get out of the field as well. But
Got it.
Yeah, the idea is they'll try to get out as soon as possible. They do have the tracking information on board, but if that doesn't work, they still want to get out as early as possible.
Okay.
Because even if it just
we just some cheers in the background here. Maybe you can.
Okay.
Oh, okay,
so
excellent.
we got, you may have heard over the intercom that science is nominal, so we're sending.
So what is that? Everything's normal?
That means they're tracking the star and can confirm they're tracking the star is what is my guess. I don't know the details of everything they're doing, but it sounds like everything is operational.
So they're in space right now.
They're in space right now. They're measuring nitric oxide as we speak. Yeah.
Excellent. Getting information we didn't have before.
That's right.
Help us understand a little bit more about its relationship with the ozone layer.
Yep.
And what was, well, I was just curious for myself what was going on in here while I was out there, but obviously they all got to see it.
No, right.
So
well,
you could fill me in later on that.
Well, yeah, we got a nice image of the launch. I mean, it was as you predicted, it was very bright.
Yes, it was bright.
As we knew,
being out there to hear the delay.
The delay, yeah. Did you figure out how far we are away?
Plus 4 minutes.
By counting how long
By counting,
it took?
yeah, did you?
Well, since I didn't know the barometric pressure, I couldn't get a very accurate representation, so I didn't bother to try.
Right, yeah, well, that's good.
I got the sense it was a couple of miles.
It's about 2 miles. Yeah.
Okay, right, but that's because you just told me that yesterday.
Right.
But yeah, that was interesting. So
go ahead.
I'm thinking maybe one more time. Let's roll the video about what the point of this mission is.
Sure.
As we've got, we're about halfway through it right now.
Right.
And
GPS.
So you can give you a little update on what this is all about.
260.49 kilometers.
sounded like their apogee was nominal.
Okay.
As well.
Excellent.
Because they were expecting 260 kilometers and they did
Yeah. Do you want to stay live here?
No, that's fine. That's fine.
Okay.
Let's
all right.
watch the video.
Great, Daniel. Whenever
lock drops.
it's convenient for you, that's all right. I'm just sitting here killing time. Sorry. Welcome to the world of video.
Yeah, right.
And then. All right, here we go.
We're trying to measure a chemical, nitric oxide, that's created by the aurora and grows to large abundances in the polar night. We want to see how much there is and where it is, where in altitude. What's really interesting about this is we've measured nitric oxide all over the globe, but we usually measure it using techniques that involve sunlight. And nitric oxide is created by sunlight. It's also destroyed by sunlight. But interestingly, it's created by the aurora as well, and the aurora occurs in darkness. And at high latitudes, you have the long polar winter. And because we're using starlight, the way we would normally use sunlight in the rest of the Earth's atmosphere, we're using starlight as the light bulb. We need a star to be in exactly the right geometry. It needs to be in exactly the right place.
We'll be using algenib on this mission. We're using that star because it's bright in the UV, and we need a UV light source. The payload has a UV spectrograph, which it measures light, UV light, at this particular color we need that is absorbed by nitric oxide. So we'll be looking at the star. It'll be filtered through the atmosphere, and nitric oxide will absorb a lot of that starlight. And how much of that starlight, the color it absorbs at, that'll tell us how much of it's between us and the star, so how much is in the atmosphere.
But there's a lot of physics between the creation of the NO and the destruction of ozone that we just don't understand. So measuring the nitric oxide, measuring the altitude profile, it's going to help us understand that, and that's what we're after.
Radar reacquired.
All right, so that was Dr. Scott Bailey, who's principal investigator from Virginia Tech, and Dr. Justin Karstens, co-investigator from Virginia Tech, about what the mission is tonight, which got about a minute left. Rocket's probably falling down back to Earth right about now.
Right,
so we got all the data that we were hoping to get.
Hopefully it was all a success.
But before we get too far into that, I want to introduce you Dr. C. Alex Young, Associate Director for Science in the Heliophysics Division of NASA's Goddard Space Flight Center, is joining us. First time in Alaska. Thanks so much. You just saw the rocket launch?
Just saw the rocket launch.
Tell me your thoughts about it.
Oh, it was fantastic.
Yeah.
Yeah, it was amazing.
Yep.
It was amazing. My first sounding rocket launch.
Okay.
So, hey, this is one of the reasons I came here.
Yeah.
I'm excited I got to see it.
Yeah, and so tell us a bit about what you do for NASA and what your mission is.
Okay. Well, I am a solar astrophysicist, and in particular, I study space weather. I study solar activity and how it impacts the solar system, everything in the solar system, other planets, smaller things like asteroids, comets, but also how it impacts us and how it impacts our technology. But more importantly, I'm here because I'm the principal investigator of the NASA Space Science Education Consortium. So a consortium of scientists and educators around the country that were centered primarily at Goddard, but we have partners everywhere, and one of our primary partners is the Geophysical Institute here at the University of Fairbanks, Alaska.
Yeah, awesome. And, you know, we had this, you and the Geophysical Institute had this event at North Pole Library here in the interior, which is about 20 minutes southeast of Fairbanks, if you're not familiar with, if you're not from Alaska. And the response was insane. There was nowhere to park.
Yeah, we had about 400 people.
Yeah, I ended up parking in a fire zone behind the building because that was like the only place I could find. And it makes me wonder, based on what are your impressions of people's interest in science, in space these days? Is this a hard sell for you, getting folks interested about what NASA's working on? All right. We're getting some round of applause.
Back there, so.
Successful mission. Okay, excellent.
All right.
If he wants to come in here and talk at any point, let him know he's welcome to. But what is your take on people's interest in in NASA these days? Because it's...
Well, people are very engaged about NASA and NASA science, but I will say, hands down, the folks around here are super engaged. I mean, I cannot tell. I mean, you were there, obviously, in your spacesuit.
In my spacesuit.
And people were super engaged. And then we were, you know, it's freezing outside, and we were at this little small town, and there were 400 people there. That was amazing. And being in a place like D.C. or Baltimore, where I go to a lot of events, that was a fantastic turnout.
Yeah.
Fantastic turnout.
Can you
give me a
status
people
of
are
the
really
iridium?
engaged. People are really excited about
CM, this
space.
is TM. We are
They're
currently
excited
getting
about
messages coming in.
the Earth and all the things that NASA does and all of NASA's partners and how we can get a better understanding of our place in this planet, our place in the solar system, and our place in the universe.
Right. I was thinking, you know, yesterday, just about how sometimes I think I don't know about you, but maybe we take a little bit for granted the how incredible it is. But what we did just tonight, we shot a rocket into space, pointed the thing at the star, measured this stuff. I mean, when you think about, we only learned to fly like 115 years ago.
Oh, I know.
Is there still a sense of like, I can't believe we're doing this?
It amazes me. I mean, to me, the engineers that do this kind of work are magicians.
Yeah.
I mean, the things that they do. I mean, I love the science that I do, but I can't even begin to do the kind of things that the engineers and the teams. I mean, this is such a team effort from the smallest rockets like this, which take, you know, many people, to the biggest rockets you can think of. All of it is about a team of incredible people who do every aspect of it to make this happen.
Of an incredibly complicated thing.
Incredibly complicated
that
stuff.
could go very badly. Everything goes smoothly.
Yep.
Nobody gets hurt. We get some incredible data, and we're going to know a little bit more about
a little bit more about
the universe,
our planet.
And our planet,
Exactly.
Excellent. Now let's talk real quick about the lecture you've got coming up now tomorrow night at Raven Landing. If folks are here in the interior and they want to meet a lovely guy who actually works for NASA, which I'd love to talk to you about what that's like at some point. Is it good?
It's a dream job.
I just have one check from NASA? Could you hire me to do something like take out the garbage at NASA? I just want it that says NASA, Rob Prince, $1.95. I might, doctor it a little bit, but anyway, yeah. So, but first, I want to, for the folks here in town, you got this lecture coming up. It's 7 p.m. at Raven Landing.
That's right.
In Fairbanks tomorrow night.
Tomorrow night.
And what are you going to talk about?
Sunny and a chance of space storms.
Nice.
Yeah.
Okay.
So I'm going to talk about this whole field of space weather, all the crazy stuff that happens on the sun, the crazy environment that it creates in the solar system, and how that impacts our daily life, what that tells us about how we are here, why we're here, the evolution of life in our solar system, and even what it tells us about the possibility of finding life on other planets outside of our own solar system.
Wow, excellent.
Yeah.
All of that and for free?
All that for free.
All that for free.
Yeah, all you
if you call now.
Is come to Fairbanks, Alaska.
That's all you got to do. Once you get here, Raven Landing, across from the library, over on Cowles off of Airport Way. And check that out at 7 p.m. And then, yeah, just real quick for me, what's it like working at NASA?
NASA is, well, in the vernacular of my friends in New England, it's wicked cool. It is wicked cool.
And why?
Well, they just do such cool things. I mean, they study everything, and I mean, we get to sit and look at data from billions of light years away, from things that were created at the beginning of the universe to looking at the aurora out the back door here and figuring out what's happening at the sun. Explosions are happening on the sun that have enough energy to power the world for 100,000 years.
Wow.
And these are happening all the time.
Right. Yeah.
And all this stuff goes on at NASA. People there study volcanoes on other planets.
I'm going to have RTD and RCV stop the recorders
Right.
if that is okay.
I know.
That's fine.
One of the things that just fascinates me is, I'm interested in time travel, and to think, like, oh, wouldn't it be cool if we could time travel? We can time travel right now. Go outside, look at the stars.
That's right.
You're
looking back in time.
You're looking back in time,
Isn't
millions
that cool?
of years.
Yeah.
And I think it's just some of the things that people look at the stars and they think, oh, cool, but they don't realize you're looking back in time. Unfortunately, it's just
That's right.
a little
Well, even
light.
when we look at the sun, when we wake up and look outside, the light we're seeing was 8 minutes ago.
Right. Awesome. All right, Dr. C. Alex Young, Associate Director for Science in the Heliophysics Division of NASA's Goddard Space Center, Flight Center. Thanks in Maryland. Thanks so much for joining us here, and welcome to Alaska. I hope you're having a good time.
And thanks to all the folks here who've shown me an amazing trip.
All
right. It's not over yet.
Nope.
No.
Not at all. We haven't taken you to Chena Hot Springs yet, I guess.
No, not yet.
That's required. All right. Well, what's our status here, Linda? We are done. Okay. Thanks, everyone, for watching. Successful mission tonight, and thanks for tuning in and for your questions. And hope that you'll join us for the next rocket launch, looking at, is it December of this year, 2020. So we'll see you then. I'm Rob Prince. This is Dr. C. Alex Young. Have a great